we have Jennifer Vlasiu of York University. She is a data science and big data instructor. She's involved with a number of initiatives, and we're going to hear from her relating to her workshop, Alternative Approaches to A/B Experiments, 3 Causal Impact Approaches.
For those of you who don't know me, my name is Jennifer Vlasiu. Today I have the privilege of speaking to you all a little bit about A/B experimentation, also known as A/B testing in the field, as well as then when A/B experimentation or testing is not an optimal mechanism, there's something called causality estimation. What is it? When can I use it? And how do I get started? So this is really a more practical offering. A little bit about me. I've been in data science and artificial intelligence for the past 10 years, working at a milieu of organizations, predominantly within the data science space, as well as productionizing AI ML models. So what's called DevOps or AI ML Ops. So what do we hope to cover today? Like I said, we're hoping to give you an introduction to the concept of what's known as A/B experimentation in the field, and why it matters, some of the challenges and situations when A/B experimentation may not be possible. Believe it or not, there's quite a few instances. And then leave you with a basic understanding of what is meant by estimating causal effects. And then we'll provide you a few alternative methodologies for causality estimation. That's been inferred from sort of big tech. So they have multiple PhDs, researchers, academics, and industry, and they work in this wonderful ecosystem of spending decades building upon a literature. And then they build that literature, philosophy, statistical techniques into something that's called a modular package that is then available to the public, like you and I, via, say, Python or R. So then I'll take you through 2 common, Jupyter and R, and how to implement a few causal impact models. Any questions at this point in time? I will take silence as let's get going. So why does A/B experimentation matter? And let me just open. So A/B experimentation, as many of you know, is the gold standard for, hold on, there's a bit of space here. Is the gold standard for estimating causal effects when you're having a truly randomized experiment. However, it assumes that your treatment and control groups are evenly distributed. And what we mean by that is that you've randomly assigned. So A/B experimentation is very popular, for example, when you're looking to understand the efficacy of a website and you add a new widget or a button. And for some portion of the population, your treatment control, you provide them that intervention. So you show them an offering with a button to help with the impetus here is that if you give them the button, they'll be able to click and spend more time on your site, versus others need to just, your control group gets given the status quo, which is you just read a series of text, and they do not receive the intervention. Now, you're probably already thinking from treatment versus control, that's a lot of foresight that went into designing an A/B experiment or A/B testing. That's not always the case. And this is not always the case, particularly when you're dealing with what's called population health metrics or quasi-experimentation. So when are situations when A/B experimentation is not possible? So they could be multiple ones. They could be some instances, for example, where it's too expensive to do the sort of instrumentation we spoke about. It could be just too difficult to isolate a treatment and control group. One that's particularly top of mind, and I'll throw in a few industry examples throughout, for example, is it may be unethical to do an A/B experimentation. And then lastly, a really common one is what we call an industry instrumentation. So in the example that I gave you with, say, a website, and I provided an intervention to one cohort group, I had to have that instrumentation set up. And when I say instrumentation, I need to have the experiment set up on the back end that I can actually track, one, the individuals that I put in the treatment group, the individuals that I put in the cohort group, control group, make sure they're randomized, ensure I have sufficient power and that the two groups are representative of each other. Then I need to add in functionality from an instrumentation perspective that I can actually track the individuals. So say that user ID that actually gets the treatment that then clicks on that button. And what percentage of those who see the button click through? Of those that click through, how many engage? So sometimes instrumentation is not done at the time and it's done after the fact. We say, oh, we did a website update. It would have been nice to know what the impact of our overhaul on our website was. But we didn't do this, we didn't make it a flight or an experiment up front. So in these situations, perhaps we want to obtain what's called a causal effect in the absence of experimentation. So like I said, you have something called the non-sampling error. Potential sources could be non-sampling error, which is just a term in statistics we use to talk about the error that can occur when you're collecting your data. There could be a difference between your cohort, your control and your treatment groups. You could have had a poor sampling method, a measurement, which is again your instrumentation, or you could have something that's called behavioral effects, and I'll get to that in a moment. But I did want to, since we do have the opportunity, I did want to spend a bit of time speaking about the unethical portion of it, because this is one that's really come top of mind recently in some of the literature and work that I've had the privilege of working on. And so, for example, when you're dealing with vulnerable population groups, if you're thinking about immigration, defense, etc. In one example, we had the opportunity to work with individuals that settle within G7 countries, and they go through their settlement reform. So numerous governments right now are looking to have AI-enabled tools to help the pathway to settlement for refugees and newcomers. So in this example, when a refugee or individual comes, we can't put them through an experiment. These are vulnerable individuals. And there's also the perception as well as reality of potential discrimination between those that are economic migrants and those that come in as refugees. And so what happens is we randomly distribute, and then some individuals get an AI-enabled pathway with a human in the loop. And we see, are their settlement outcomes 6 or 9 months post-landing superior than those who just got the normal hand-holding with a human intervention throughout. And what I mean by the AI-enabled tool, for example, is can we leverage technology to help with access to knowledge? So at least in Canada, it's, did you sign up for a health card? Did you sign your school? If you have a child, did you sign them up for school in the neighborhood? Are you aware that you are eligible for a family doctor? Have you found a nearby library or a social group? So they do a series of information to knowledge, information to behavior, and then information and then actual a change in behavior. And so this is where A/B experimentation is not sufficient. And this is where a lot of population health metrics are dealt. Similar with, say, COVID examples, looking at vaccination rates. Anything that typically tends to be population health metrics or dealing with sensitive human-centered data sets, typically, or precarious situations, this is where you'll see a lot of causal effect analysis and causal methodologies coming about. So what is meant by when I say causal effect? So a causal inference is a branch in statistics that is concerned about the effects, sort of the consequences of our actions. So we look at, it's the bedrock actually of a modern data science, and understanding that causality is really important. And sometimes it's more important than identifying the correlation patterns. So many of you in data science probably work with a correlation matrix. Causal inference is looking about that effect, is really a very interesting field to explore. So let me give you another example. So in causal inference, we seek to understand the effect that some variable has on another variable. For example, the common one that's widely given in literature is this US unemployment rate, or any unemployment rate for that matter. So say, for example, you want to assess what's the effect of unemployment on the probability that a riot will occur. And then you want to take it further and say, what's the causal effect of a riot, perhaps, in government spending? So what's this called is, it's a pictorial picture of what some might call a knowledge graph. So some of this, your hypothesis going in, you think there's a relationship between one with another. You're not 100% sure. And you haven't done an experiment in A/B instrumentation, either because it's too expensive, unethical, not possible. The issues go on. And so the alternative here is the rise of causal inference. Another reason within causal inference is something called encouragement design. So this is a term where if we're unable to force all the experimental subjects to randomly take the assigned treatment or control, this is also with causal impact and causal inference literature and opportunities come to light. So now going back into sort of our bread and butter, if we were to apply this in, say, a big tech example. For example, this is causal impact analysis is done very heavily in, say, software upgrades. You can't force, for example, if you have a Mac and you see the litany of them, all the upgrades that have taken place, or if you're upgrading from, say, Windows 10 to 11, you can't force a user to take that treatment. So that treatment could be download the upgrade option, and it comes up as a pop-up or a banner. You can't force your treatment group, which sees the pop-up, to take that offering. At the same time, you can't force users who are in the control group to not take the treatment. So there's nothing stopping a pop-up that says, download the newest Mac OS that comes up as a banner. There's nothing stopping, if I was, say, in the control group, from just going onto a search engine and searching, download the newest Apple operating system. And so what happens here, as you can quickly see, is I no longer have an A/B experimentation. I've actually tainted my treatment and control group because I have control individuals who I can't force. I'm trying to study human behavior here and consumer behavior. The term in the PhD world would be called marketing sciences. I'm looking to understand this phenomena. So why do people who don't see the pop-up, what drives them to look at, to search and seek out the latest updates? This could be your super users that sign up for they're most engaged, they spend a lot of time in the browser, they spend a lot of time on their devices, they have a certain app profile. At the same time, I can't stop people who see the treatment to actually take the treatment. So just because you see a treatment, how many actually engage with the treatment, how many then seek the full treatment? Another example for to bring this to home from a consumer perspective is marketing campaigns via notification. So how many of us have a pop-up that shows, for example, the newest marketing campaign, push to text, so it pushes to a text system or it pushes on our web browser. Users could have turned off notifications, so they'll never be part of the campaign. So this is particularly challenging now because the cohort of individuals, the type of, if you're doing a profiling, the type of user profile that turns off notifications and self-selects out from these treatment groups means that it's then not representative to say that your findings, your end impact, is representative of the entire population, if that makes sense. And so this sort of, we're giving it to you here in more from a big tech perspective, but you start to see how this can translate in really those human sensitive data sets. And so that's why I'll try straddle both so you can see how transferable these methodologies are, regardless of the industry or the data set within which you're trying to apply it. So let's get into a few alternatives and a couple of different methodologies. So one of the methodologies for causality estimation. So as I've gone through, I just want to make sure I've covered all the notes I had for you on this. Perfect. And I have covered. Beautiful. Okay, perfect. So you have sufficient understanding on all of them. So I wanted this to be sort of a cheat sheet that you can run with after. So in industry, as I said, as with all non-experimental approaches to causal inference, there are valid conclusions that require strong assumptions. So it's generally recommended that you try at least 2 different methods. And so what you're looking at here is a grid which on in the columns, it's showcasing the key packages. I see it's moved a bit from the PDF perspective, the key packages and assumptions. And then the rows, we describe the about, the underlying statistical technique, the model assumptions, and when to use. So sort of the precursor are the first 3. So the Google Bayesian time series is often used to really understand that, estimate the causal effect of a designed intervention on a time series. So it's very popular for marketing campaigns, for example, or if you're trying to see behavior over time sequentially. It's instantiated via R. And what it looks like is it will take in, it's very straightforward, which is why it's extremely popular and powerful, is essentially it takes a data frame of minimum 3 fields. Your first field would be your time series. So you're trying to track over time. Then you would have your treatment. So you would do a cohorting analysis and you would identify users that underwent a treatment, like I said. Then with those ones have been tagged, you would get key metrics you wanted to evaluate. And say, for example, you want to see the revenue of the people who clicked through. So you'd have a column for treatment, and then you would have a column for control, users who did not engage or have exposure to this intervention. And then with those 3 columns, you're essentially able to estimate how that response metric could have evolved after the intervention and had the intervention not occurred. And I'll show you what I mean by that. And to put this into practice, it might be helpful to just show you here. So for the first one, like I said, we're looking at Bayesian structural time series. It's a statistical technique that takes in 3 variables. So here's some dummy data that I've put together. You can see it's a continuous time variable. There's a pre-period and a post-period. It's a pre-period, pre-intervention and a post-intervention. And so what it does is, say, for example, we're looking here at, we'll make this dollars. It can be anything really. So in your pre-period, which is before this dotted line, you want to make sure that the treatment and control groups you've selected are normally distributed and are representative of each other. So you don't want to have implicit bias or self-selection biases within your treatment cohort and your control. So what you can see is it's called typically line of best fit. You try to look at before the intervention, how are these 2 cohorts tracking? If they track really closely, like you can see here, then this is considered a model that you could consider of a best or better fit. And then ideally, what you would like to see, hopefully, depending on the intervention, your intervention could be at that point in time, this could be revenue, or this could be an engagement score. At this point in time, or minutes spent in the browser, at this point in time, I gave them this really interesting button in the feature. And what happened is the individuals who were exposed to that engaged and spent more time, or spent more revenue. Vis-a-vis those who did not, your synthetic control, and I'll get to that in a moment, continued. And this was actually the trend line, including seasonality. And so the delta post-intervention between the observed data and your counterfactual estimate, that would be the impact you would quantify from your quasi-experiment. In this example, the marketing one that I gave the button. So I didn't fully instrument it. I'm a startup or an individual or a nonprofit. I don't have this extensive resourcing and instrumentation infrastructure. And I want to assess after the fact, how do I do that? Well, causal impact, if I'm looking for quick and dirty, and the level of complexity to get started is pretty straightforward compared to the others, it's all relative, then this might be one model you might want to consider. And when you don't really have a true control in the experiment sense, you can do something that looks like a control. And so that's what I mean by synthetic control. It's a term that's been popularized by two researchers to really just talk about it as counterfactual estimate. And like I said, the difference between the counterfactual and the actual is your causal effect. The second, and this can be instantiated in a few lines of code, and I'll get to it in a moment. The second model that you're seeing here for the Google Causal Impact is what it looks like is what's the net, the delta, right? The net delta, as you can see here, if you eyeball it, 105 to about 120, that's the net impact of 10 lift, sustained lift. And ideally, if you're doing in a flight where your metric is you want to drive engagement, revenue, volume, net promoter, time, you would want to see your point-wise, the middle chart, have an elevation after the gray, after the intervention. And you want to see it sustained. Because what happens is if you saw the started line go up and then it went down, which is actually very common, that's called the novelty effect. So you can start to see what would be interesting here, for example, is you see this lift, great, the users are wowed by this interesting, sexy new button. I'm going to spend more time and now explore this website more because they're making the user interface really great. So you see my sustained engagement, for example, but then it starts to taper off as the novelty wears off. And if you start to see this lift then drop back after, say, 8 or 12 weeks, back to the seasonality norm and closer in line with the synthetic control, then your finding would be that this is a quick win, but it's not a sustained win. You haven't actually nurtured or changed the behavior of these individuals. Taking this back into a recent example that I had the privilege of working on is within immigration and refugee and citizenship reform, which was here, we had a set of individuals on both. You get the same experience as you come in as you try to seek settlement. However, some were given an AI-enabled app, and others were given the continued human. And this was a time to reach certain milestones, like I said, time to the feeling that you're settled, you feel confident that you have the knowledge and behavior to be successful, and that you're fully aware of all the benefits and the support system that's there for you, including your ability to get a job, walk towards self-sufficiency, housing, shelter, etc. And so this is the hypothesis that we're seeking to see. And this is sort of the models that even our governments are using, nonprofits are using, and big tech is using, and professional services. So the causal impact model is really one that can be leveraged across. And now the third model is you want to see a cumulative gain over time. So all this does is it takes the incremental lift and it cumulatively adds it. So obviously you can see it goes over time. So if I was looking back to business, if I was looking to impact, say, engagement scores, revenue or volume, this might be a very, I would want to see my point-wise be sustained. If, however, this was the effect of my cost structure, then there might be some concern here. So this is the Google Impact one. It's a Bayesian time series, and the delta is being the net impact. Like I said, what I wanted to bring to your attention actually is that there is, this is done on Bayesian time series, but there's also an MLE version. And so what happens is it's just an underlying different statistical technique, but over time they converge, and the delta between the two is actually about like a 1.1% variance. It's just that all the logic, and this is just a general shout out, a lot of the statistical techniques and the packages were designed in R, and now as Python becomes more ubiquitous and we're seeing a lot of these econometric techniques also being built in Python, when you do the rebuild, it's not always a one-for-one. And so this is one of the packages I wanted to call out. Now, the key thing with this is the Google Causal Impact assumes a graph, and I'll get into it in a moment, what is deemed by a knowledge graph. And then you would use this when a randomized experiment is not available, or when you're seeking to understand those causal effects. What would have happened in the absence of that action? So this is a what if scenario. What would have happened now? What was my lost opportunity? I only did it on a small treatment of not having that button there to engage users further. It looks like the foregone opportunity, which is that net impact, is the opportunity cost. And then I've provided just on the next page, if I go and I wanted to show it. Oh, am I still sharing my screen?
Yes, you are, Jennifer.
Oh, perfect, perfect. I wasn't sure. So if you look at the Google Causal Impact, I wanted to just show it here. You're able to get started, and I'll take you through it in a moment, on the response metrics. This is the first one. The second one that's really come out, and it's become a showstopper, not to geek out about it, but another really exciting one that's come from literature has been Uber's research team. So they spent a lot of time, particularly within their Uber Eats function, which is interesting, on campaign targeting optimization. So for them, they look at uplift modeling and causal inference methods using machine learning algorithms based on recent research. So they look at what comes out of KDD, which is a popular research forum, and then they see how can they apply that literature to sort of their business problems that they're solving. So what this one does is it looks at the estimate the causal impact of an intervention, say T, on an outcome of Y for the users that they observed over a feature. So they do numerous in-app features. And then they look at the treatment effect, and this I wanted to call out, both from an observational perspective, so over time. So they didn't actually discriminate. Say, for example, when you do a software upgrade sometimes, everybody gets it. Or you do an app upgrade, everybody has access to it. So it's observational. What kind of person upgrades, how does their engagement level drop off post-upgrade, or is there sustained lift? Versus experimental data, which is before I even do an upgrade. Perhaps I want to test and understand the user's behavior. So I would run an experiment, say 1% of my app cohort, or up to 5, I would see what's statistically significant. And then based on that experimental data, I would then roll it out to everyone. So it's interesting that it looks at both. And then it does, what happens is something called conditional average treatment effect. So the conditional average treatment effect is an individual treatment effect is applied for experimental and observational data. And what's interesting with this model versus Google's approach is there's no strong assumptions that there's some sort of relationship, that there's some sort of hypothesis or embedded hypothesis going in that the user is going to behave in some way. So it's very popular in campaign targeting optimization. So when they're doing their ad campaigns, they're looking for individuals that have a favorable response on a given KPI, like engagement or sales. So they look at historical things, features. For example, time spent in the app, basket size per order, and they start to actually do what's called cohorting. So they'll do a random forest or an XGBoost, and they'll start to cluster users, and then they'll run different treatment effects for these different cohorts of individuals. And those cohorts of individuals have been selected based on some sort of a clustering algorithm that has focused on key features that they have known are closely correlated to certain KPIs. So with this one as well, there's an uplift modeling and causal inference. Let me show you where that one is. So all the literature as well here, and it gives you lovely literature on it from experimental, like I said, campaign, as well as personalized. And here are some typical decision tree or tree-based algorithms are used. So they take a machine they take a machine learning approach. Google's Causal Impact takes more of a stats or econometrics approach. This one takes a machine learning approach. And the other thing I wanted to tell you a little bit more about it is there's different algorithms that you can take where the learning rate is different. And so that's what you're seeing here, as well as instrumental variables that I'm trying not to get too much into. But you can have a read through the literature and it can show you the importance, say, of treatment versus a feature. So for example, this treatment could be, like I said, we're going to upgrade the app on Uber Eats. And what are the features, the most important features that we're going to focus on post before for that treatment group? Was it time spent? Was it on iOS, or is it an iOS app, or is it on an Android? They could look at things on if the device is registered as a corporate versus consumer device. They could look at numerous different metrics and see what the treatment effect is. Now, the third one, which is sort of the third big tech sort of causality estimation that you can give a try, something called Econ ML. So this one actually comes from the Alice. It's a Python package that applies the power of machine learning to essentially estimate the individualized causal responses, both from an observation and experimental data. And it does this again via machine learning techniques and econometrics, but it's really the difference between Econ ML, and again, I put a disclaimer on all of the slides. All information and logos are publicly available, and none of the information I'm giving you today is to be misconstrued as sort of an official stance or position of any company or individual party referenced. This is just a perspective from seeing what's in industry. What makes this one very interesting compared to the Uber one is, as you're working with it, is yes, it's got similar functionality, like it does have the conditional average treatment effect estimators. But what's really neat about it is that we're able to actually measure the causal effect of some treatment variable T on an outcome variable Y, but we're able to add a controlling factor. You can have a feature of controls. So you want to normalize for some of the noise. And like I said, they do a lot of random forest-based estimators and instrumental variables or deep instrumental variables. And what's really interesting about this one is it's got a very flexible module. So you can import sort of the packages they've built, or you can rip it apart under the hood as you get more comfortable and hyperparameter tune those modules yourself and import them as packages yourself. So it's got a bit of both. But by and large, these are three packages and libraries that you would import. They've already done a lot of the hyperparameter tuning. If you were to build these all bottom up, you import them, and then you see the results. And that's why we say try at least two methods. So you two different methods, because the hyperparameter tuning for each business has been done a bit differently based on the business's express needs. So that's why I say look at the when to use for sort of a pattern recognition to see whether or not there is some sort of transferability. And the similarity between the two is this notion of the conditional average treatment effect, which is the causal effect on an outcome of, say, an interest Y, and then switching that treatment value. And lastly, within the Econ ML, you can look at outcomes, you can look at treatments, features and effects, as well as various instruments. It gives you an estimator. You apply some test features, and then it tells you what that effect is. And let me pull up, where is this one? This is Econ ML, Microsoft. And I just wanted to bring this one up for you here. So you can bring it up here. Just loading, give me 1 second. I find that their actual Microsoft.com page describes them a little bit better for you if you're looking to understand. But typically, like I said, it's for recommendation. So the recommender system, that's why customer segmentation, so similar to Uber, they'll try to segment, and then multi-investment attribution and looking at those links. And then you can go straight to their GitHub, instantiate it. So via your Jupyter Notebooks, or if you're using Azure ML or Visual Studio, you can just call it in. And this is their research on here. So this is the third one. Now, the first three are sort of packages that you can use to work with causality estimation. The other two that I wanted to bring to your attention are what's called wrappers. So these are sort of an end-to-end library for causal inference. They encompass, so if you think of it like a superset, they sit on top and encompass all the different packages that you can get from Google, Uber, Microsoft, a litany of others to do causality estimation. Then they add explainability to it via a neat API, and then it helps you to evaluate these causal models. So when you're looking to get started, you can go one of two ways. You can go bottom up, so one by one, instantiate each of these modules and packages, Google, the time series, the Causal ML and Econ ML. Or alternatively, you can just get started with, say, the DoWhy package or IBM's causal library, which is also very neat, given that they consider more in different disparate industry use cases. And so with that one, I wanted to just showcase as well for your consideration. So they look at outcomes from real world as well as from non-experimental information. And it provides you causal interpretability, so you can actually interpret the Kate with trees and SHAP values. Both these APIs, one is done with sklearn, the other is an end-to-end that embeds really nicely with Econ ML. Both of them can be integrated for sensitivity analysis, and it's called doing causal validation. And they can both recommend interpretable personalized treatment policies for you. So based on this, I wanted to get, if the cheat sheet of getting you started, so to speak, is still a bit too nebulous of a notion for you, I wanted to show you a few concrete steps on how you would get thinking through this. So like I said, the first two packages, they've already embedded their own knowledge graph. They've already embedded their own knowledge graph as part of their design. However, what it's assuming is some of them assume what's called a direct or indirect graph. In knowledge graphs. And then from there, typically what's helpful to get you started is try and have that hypothesis. So which direction does, for example, an increase in unemployment, we hypothesize will lead to an increase in social unrest, okay, to B. And then we think there from B, this will lead to an increase in security spending or infrastructure spending. That would be a directed linkage that you're going through. And that is just documenting the relationship. So frequently, who would speak about knowledge graphs would be people like programmers when they think about networks. And graphs for them, and for many people, they just, in a common sense, they help with like figurative representations and help you imagine different groups. It also helps infer sort of the data structure that you're going to be dealing with. And so step one is always, when we say knowledge graph, it's not an actual graph. It's showcasing that causal relationship. And then step two, which could be an entire workshop in and of itself, but I want to be mindful of time, is looking at the different, is to make sure that your assumptions, like your hypothesis, the example that I showcased at the beginning, if there's a rise in unemployment rate, the common consensus is they may or may not be a rise in riots, which means they may or may not be a rise in spend. How do I validate if that holds true? Correlation versus causation. It's something called, you can validate them using many kinds of identification methods. So many of you may have heard of graphical constraint based methods or non-graphical constraints. So graphical assumes that there is some sort of relationship that operationalizes between them. And you can search those through after, and I'm happy to share more resources. And then where I actually spend a lot of my time, because it's in nebulous population health sort of metrics, is this identification of additional non-graphical constraints. So we look at a lot of diff of diff, instrumental variables, and regression discontinuity. So you could implement those. Again, those are available online. And then if you see that your assumption holds, that okay, this works, you set it up correctly, then consider step 3, selecting which causal impact package you'd like to get started. And then finally, we believe that you can use the wrapper, like either IBM's Causal Library or Microsoft's DoWhy. Both actually do a really good job at believing that the right level of abstraction for causal analysis can, how do we say this, can help lay an equal focus. So in the end, both of them provide sort of an end-to-end library for causal inferences, and it helps to organize your causal analysis around sort of those 4 key steps. So you'll see you'll bring in a model, which encodes sort of prior knowledge as a formal causal graph. So it's well integrated with DoWhy. So you bring in your model, which will encode that prior knowledge. Then you could use something called identity, which uses that graph-based method to identify if there is a cause or effect estimate, which you can get through step 2. And then you have that estimate, like I said, which is either your Kate, your late, which uses that statistical method for estimating the identified estimate. And finally, you have that level of refusion, which is obtained, which is an estimate for testing sort of how robust your initial assumptions are. And that will come to fold, if you saw in the picture, and I can take you through them now, sort of that line of best fit. So how robust is this model in meeting the needs and the various assumptions as you continue to tweak and as the data continues to evolve and user behavior continues to evolve. So in summary, like I said, wanted to just make you aware of 1, what is A/B experimentation? 2, when might I go wrong or not wrong? There might be other alternatives. And if so, what is this causality, causal inference, this estimation? How can I use it? And if I'm going to explore, I could get lost very fast. Where's sort of my grounding that I can get going with sort of in my little toolkit, 3 go-tos from even level of complexity, level of left to right, level of complexity, perhaps one could argue, for deploying, but also from left to right, then level of robustness for the first 3. And then you have these 2 libraries that can provide you flexible modeling and high tweaking. So these are APIs that then can help you hyperparameter tune these even further. And if you want to get started, these are your high level steps. So now let's walk through. I think we're going to be a little bit tight to take you. I started putting them in. Let me take you through sort of a sample walkthrough on how you would install it. And then there's also the notebooks available as well as in the GitHubs. So the first thing we ran through was literally you would do from Conda. You can either, if you're doing Anaconda Navigator, you open up your terminal, you do Conda and you can pull the Causal Impact package from the GitHubs directly. All of them, I believe, showcase this. Let me just check. All of them do show this. Yes, you can import directly from Conda. So in your terminal, you would pull these through. Another alternative, so once you have it, then you call it through, say, your interface. I'm just using, this one is done in R. Then I'm calling the Causal Impact package, which is within that GitHub. I call the library once it's installed. And the sample data set that they're using is they set the seed using an ARIMA model. ARIMA is similar to, say, the Facebook profit model. It's very popular in day-to-day forecasting on a time series, say, units of sunblock, for example. So once you have it, what you're looking at, like I said, is you have here, you have your index. I prefer not to use an index. I prefer to usually use a date, but indexes work too. A lot of the data sets we tend to work with we're doing a lot of different things, like we're looking at causal effects by month, by day, by time of day, by rounded to second, but you can have it by index. Then, like I said, your Y variable would be your treatment, and then your X1, your control. So once you have here, you're installing the package, you've created the sample data set, and then usually what you want to do before you do a quick little bit of EDA, just to see how your treatment, your Y and X1 are tracking over a function of time, for example, and their lifts. So what you want to look at is it's okay if there's even a gap, because you might have fewer, but still stat sig, treatment versus control. But what you want to see is before the intervention, that's sort of the trend line between them, is they're behaving, the two cohorts of individuals, groups, treatment and control, are that you've denoted in this instance, are behaving within the same pattern, because then you know that you've actually selected appropriately. And you're not actually embedding or perpetuating a sample bias or a bias within your analysis by, for example, already selecting very engaged users who would have clicked anyway, if I go back to that click example. So then you run your analysis, and this is the beauty of it. It's really, you denote a pre-period, like I said. What's that period? You pick in this instance, they're picking an indice. So they have the entire list of 1 to wherever. They're picking the indice at index 70 of that time horizon. That's when the intervention takes place. Then post, in this instance, an intervention could actually be one data point, 1 day, or it could be a series, it could be a month. For people, for example, upgrading, you want to give them that opportunity. And then your post intervention period, which is 71 to 100. Then, like I said, you bring it in. This package, as you can see, we're passing it through from calling it impact. This package, Causal Impact, the hyperparameter tuning behind it has already been done. So it's it's not a black box, but it is a package that's been developed that you can leverage. And then if you want to do further explanation, that's where I said you can maybe explore IBM's causal library or the DoWhy. But you're bringing in, it only takes in 3 parameters as a requirement. So that data set, your pre and post period, and then you're able to visualize it. And by default, you'll always get these 3 panels. Like I said, your first one will always show the data and the counterfactual. In the pre and post period, your pointwise will be that causal effect, which is your second estimator. And then your third one is always going to be that contribution. I've explained it a little bit more here so you can understand. And this would be pre-period. This would be post. I'm just trying to be mindful of time. And now you are able to do some hyperparameter tuning, for example, from a time series perspective, if you want to do anything with the data. So you want to feed in, bring in the data, which I typically do. I bring in data, so then I denote it. You're just converting it to, instead of your index, you're converting it to a date. And then you're plotting it. Now, the summary, you always want to print a summary table where you want to look at the standard deviation, the 95th percentile confidence interval. And here is where you would actually see what the intervention was. So I need to confirm, no deny. If, for example, the web click example, this would show that there was the range was there was a 9.8 to 11% lift in revenue within the treatment control, the treatment versus the synthetic control group as an absolute. And the range, the upper and lower bounds, those are impacted by a couple of things. If your bounds are too large, that might be an indicator that this model that you've selected is not necessarily the most appropriate model, or there's not too much confidence. If it was between 9.8 to say 23%, it's very difficult to then demonstrate sort of the success, especially if you're making business decisions on them. And so you wanted to make those upper and lower bounds as more concise as possible. And you can do that by doing a series of hyperparameter tunes. It's called adjusting the model. So typically what I recommend is that the best practice is you want to have at least 1,000, 5,000 iterations. So When you run it, instantiate causal impact, you want it to run, and the confidence interval it gives you is not just a one-off. You want it to look at that fit, the underlying behavior, at least a 1 to 5,000 times. And then in my instance, the n seasons is looking at that seasonality of it. So I look at it, I typically use 7 for a 7-day-a-week component, because I want to look at how it's doing, not just on a daily. I start to sub-bin by weeks to start to see, is there some sort of behavior in the first week versus second versus third versus fourth. Another way within the model arguments that you can pass through is when you're doing the pre and post period, if you change your post period, because you're seeing the novelty effect, like there's an unsustained lift, you could then pick a post period where you just want to see how is your pre-period versus, say, the 4th week post or the 5th week post. Or from the settlement example I gave you, how are individuals not doing just 3 months post, but 9 months post settlement? What are their outcomes? How is their feeling of safety? How's their feeling of acclimation? How's their feeling of wellness? And their demonstrated intents? How is that looking at 3 months versus 9 months? And you can just bin it that way. And like I said, if none of this works for you, there is always the opportunity to create your custom models by actually going, since this is an R, to CRAN, and you can actually just look at the BSTS, the Bayesian Structural Time Series package for non-Gaussian error families and observation. Read the literature and actually tweak that. And then you import that tweaked version as your causal impact. Same parameters you're passing through. Here are a few helpful references and links. And now before we go, I just wanted to show you one that I felt the GitHubs didn't do justice, that I did provide as a sample. So you have the 3 where there's a litany of information, and in the Uber one, there's also here a sample notebook that we've leveraged, that you can leverage as well. But I did put one together for the IBM one, just so you could bring it in. So you can bring in that one. So I brought in the IBM one that I wanted to take through. So essentially, you would just do your pip install causal impact library. You would import, once you import it, the IBM one, you just have pandas and NumPy, and then it loads a series of functions and covariates. So you let it load all of them based on the Kruger method. And once it's loaded, in this instance, I just brought in a dummy data set that's available online. So this would actually work as well for you, where I wanted to look at a function of wages in the fine dining experience and see if, based on wages, starting wage, your month, and your usual first raise, and a series of other features like your branch at Burger King, the branches at KFC or Wendy's, what are those implications? And what's the change of employees by fast food restaurant? And does a starting wage impact the change of an employee retention by these fast food chains? So then what you can bring in, like I said, we spoke about a series of evaluators that you can import, and then you can hyperparameter tune them to your satisfaction. And there's further literature as well. But I felt that getting started, it wasn't as easy, even though the IB one's actually pretty neat. So I'd recommend checking it out. And so what you can start to see is you can look at the wage, the time by state. I've grouped it by. And now here is very, very similar. The IBW, the weighted standardization from sklearn. All of these estimators are available in the other packages as well. The degree to which you can hyperparameter tune them, though, varies by the package that you instantiate. But most of them at its fundamental, if it's a categorical variable, the underlining for causal effects, it's using some sort of logistic regression. And if it's your target numeric variable, it's a target numeric variable, then it's going to be using some sort of linear regression. So if I'm looking at revenue or units. And so I can learn those with all my estimators, make various adjustments, and see how my line of best fit is, as well as look at my upper and lower bounds in my confidence intervals to see if this is an appropriate model to use. And so I pulled these all through. I know we're running out of time. You can plot to look at the marginal estimators, look at the covariant balance if it's weighted or unweighted by key features. So I just brought in a few covariates here. Look at by different estimators. How does it vary? And so that's the same sort of thing we did with the causal impact for the first three. And typically what we find is your midpoint. If you're ever looking at a range in implementing, your midpoint tends to be the same, but just the hyperparameter tuning will change your upper and lower bounds. So that's just a best practice we've learned. So I know we only have less than 3 minutes to go. So I'll open the floor now if there's any questions. I haven't had the opportunity to look. And let me see. And I'll pass back the floor.
Thank you very much, Jennifer, for the insightful workshop. And you do have a few questions in the Q&A panel. And as you pointed out, I know we have a few minutes left. We have in the series Causal Impact part, do we get the synthetic estimation before the actual event, then over time get the actual observations and compare? Or do we start with the whole data, then do the calculation?
If I'm hearing right, I'll ask just for a clarification. So typically what you'd want to do is you have all your data sets. It depends on when you've started. So if this has already happened, this intervention has already happened, for example, in the most common instance, and I am still sharing, correct? Yes?
Yes, you are.
Okay, perfect. So if this is already, and that's why I come back to this, if this has already happened, so say, for example, you wanted to see what the impact of Apple Mac OS history was. So this was actually a real use case. And you want to see how the Big Sur version went, and it's already taken place, you would have historical data. So now it's too late to have done an A/B experiment. It's already happened. If it wasn't done at the time, if everybody was invited for the upgrade. What you would then do is you would go in and you would see you would try to understand, you would take the treatment is the individuals who actually upgraded versus those who didn't. And then you would look at what are the features post-mortem, you would look at what are the features where there's sufficient likeness between the cohorts to make sure it's a normal distribution to bring into a treatment and control, and where are the variations. If it's day and night, then you might not be able to do causal effects at all because it's gone, and the two groups were so fundamentally different that it is difficult to isolate that it was only because some users upgraded. You would want to look at what's called their telemetry and look at seeing, was there a pop-up? Could we see if who was part of, say, a campaign? Who was part of a campaign or not, would be one way to do it. Another way to do it is usually there's logs. And so if you know this is about to happen, you can, and instrumentation is too expensive, or you have issues you have some sort of, it's too expensive. Another way you can do it is design it up front before you know some sort of interventions. So you know you're gonna do a new version of Chrome, for example, and you're going to do a marketing campaign or a pop-up for 10% off shoes if you're a shoe company. You know this is about to happen, so you already want to tag the users in the back end, tag the users that you're going to follow their life cycle or their behavior patterns in the pre-period as well as in the post-period. And then you're going to tag the people that you're not going to do anything to them and provide them a control. And so once you've tagged that these people are going to be part of your quasi-experiment, you're going to show them this marketing campaign. In this example is this pop-up. Then you'd be able to see what the delta is. And you could very easily, based on those tags, feed it into a causal impact model and have your treatment and synthetic control. And I know I'm 1 minute over, so I do apologize. Thank you very much for having me.
Thank you very much, Jennifer. And I know that there's some other questions. We can always follow up offline.
Of course, of course. So I'm happy to add my my email in the chat, and feel free to reach out if you have any interest. Again, the subject matter, this is very applicable anywhere from business all the way to population health. Thank you.